Welcome everyone to the Next Gen 4 International Forum webinar presentation. Today's presentation on revolutionizing nuclear engineering education, developing virtual labs for neutron detection, Geiger counter and reactor experiments will start in just 1 minute. Doing the introduction today is Dr. Patricia Pavier. Patricia is the chair of the Gen 4 International Forum Education and Training Working Group. She's also the National Technical Director of the Molten Salt Reactor Program for the Department of Energy, Office of Nuclear Energy. Patricia.
Yes, thank you very much, Bertha. Good morning, good evening, everyone. It's a pleasure to have Mr. Jonah Lowe with us today. He's an undergrad nuclear engineering researcher and a student at Purdue University in the United States with hopes of starting his own company. In the past, Jonah has worked at an unmanned aircraft system startup called Avetics in their R&D department, developing drone applications contracted by companies such as Shell Oil and Gas, Petronas. His current aim is to deliver nuclear engineering places where it is needed the most. He likes to read on game theory, metaphysics, and social science research network. I would like to add also that I met Jonah almost 1 year ago at the Conti 2023 conference, which is a conference on nuclear training and education. I've been very impressed by his presentation and the originality of his talk, and that's the reason I invited him to present today. So Jonah, thank you very much for being here, and we're looking forward to hearing this presentation. Thank you.
Okay, well, thank you, Dr. Pavier, for the introduction. And I would really like to thank the Gen 4 International Forum for inviting me to speak at this webinar. But most of all, I'm extremely humbled and excited to be presenting our team, the virtually integrated labs work of the past 1.5 to 3 years. And before we dive into what we have developed for this community, it is crucial to state why we do what we do. Okay, so let's jump right into it. So as we all know, the UN Climate Change Conference, COP28, happened this past November to December in Dubai, the UAE. And I think it really resonated with us all in the nuclear community that countries launched a declaration to triple nuclear energy by 2050, right? So recognizing the nuclear's key role in combating climate change and reaching net zero greenhouse gas emissions. But what does this mean? And what does this mean for countries that declared this declaration? And how are these countries, how are we going to get there? Well, first of all, I think we should look at the country that is leading this effort as an example. And so this is a map of the United States. The United States leading this effort. And on this map, we have dots indicating the number of nuclear power plant sites with 93 reactors currently operating. This is the largest national grid in the world in terms of nuclear power and electricity, with a capacity of approximately 100 gigawatts of nuclear electricity. It was built first and fastest over 20 years. And this was around 5 gigawatts of nuclear electricity added to the grid per year during that period. So if we were to triple this, let's do some simple math, right? So currently we have 100 gigawatts of nuclear electricity. If we were to triple that by 2050, doing some simple math times 3, that brings us up to 300 gigawatts of nuclear electricity. And so that's a surplus of an additional 200 gigawatts of nuclear electricity. So we double the added nuclear electricity per year compared to the 1970s to the 1990s. So that would require an additional 10 gigawatts per year of nuclear electricity added to the grid. But this is pretty optimistic. This is an optimistic number, and we have to be a little bit more conservative. As we all know, nuclear power plants have an average lifespan of 40 years. Hence, we would then have to take into consideration that by 2050, approximately 100 gigawatts of nuclear electricity will be decommissioned. Hence, we would need a surplus of 300 gigawatts of nuclear electricity. Hence, an addition of 15 gigawatts of nuclear electricity per year. So optimistically, we would only need around 10 gigawatts of nuclear electricity per year, but more realistically, we would need 15 gigawatts of nuclear electricity per year. So 10 gigawatts of nuclear electricity, 15 gigawatts of nuclear electricity. The Department of Energy here in the United States found a middle ground, and we are looking for a 13 gigawatts of nuclear electricity added into the grid per year. So what does this mean in terms of workforce development, right? So over the 1970s and 1990s, we have 5 gigawatts of nuclear electricity added into the grid. Well, in the next 25 years, we would need 13 gigawatts of nuclear electricity per year added to the grid. And this is no easy feat, as you know, the United States, debatable or not, is not a manufacturing might as it once was. So let's look at some numbers to really delve into this. Our current nuclear fleet workforce consists of around 100,000 personnel. And according to the DOE, the Department of Energy, by 2050, we would need 100,000 people in operations alone. This brings about a few questions and concerns. First of all, how are we going to train the amount of new nuclear plant operators in the size of the current nuclear fleet workforce? And how are we going to get people up to speed quick enough, right? We're talking about generation 4 reactors, such as gas-cooled fast reactors, lead-cooled fast reactors, molten salt reactors, supercritical water-cooled reactors, sodium-cooled fast reactors, and very high-temperature reactors. These are generation 4 reactors, and not just what we have currently, such as PWRs, pressurized water reactors, or BWRs, boiling water reactors. So with this in mind, generation 4 technology, our training tools for the nuclear workforce development need to be generation 4 as well. So we've got a few challenges here. And with challenges come opportunities. So let's look at the most recent challenge that we face, and that is the COVID-19 pandemic. As we all know, most education, and specifically nuclear education, had to go remote. Classes had to go online, labs had to be canceled, and even some university research reactors had to be shut down as well. Well, this is Dr. Stylianos Hatzidakis, and he is the director of nuclear engineering radiation labs here at Purdue. And he saw opportunity in these challenges. And in essence, he laid the foundation for what we are currently developing here at the virtually integrated labs to cater for these challenges. And let me show you what I mean. Okay, so this is a survey meter lab, and it is one of the first labs that students undergo in their undergraduate radiation lab curricula. And it is an essential lab in terms of training students when it comes to radiation detection. And it's utilized everywhere in the workforce. As you can see here, these are lead bricks in order to prevent bystanders from being exposed to unnecessary radiation. This is a needle source providing substantial radiation. These are attenuation materials such as wood and paraffin. And this is your typical survey meter, a Geiger counter. So in this lab, students can expect to learn the dose rate equation, the attenuation equation. So in essence, learning the dose rate, inverse square law as found in the dose rate equation, the mass attenuation, using different gamma sources such as cesium-137, sodium-22, and cobalt-60. So Dr. Hatzidakis took all this and formed the very first virtually integrated labs project, so students could at least learn and experiment through their personal computers remotely during the pandemic. So this was it, the very first build of a virtual Geiger counter lab. And this lab was fully accessible to students through a web browser or a link. So as you can see here, this is a virtual Geiger counter. This is a virtual source. You've got variable distance using different sources, different attenuation materials and combinations, and you would get a dose rate out of it. So we developed this and we asked ourselves a few key questions. Basically, lessons learned and reflections from COVID education and innovation. First of all, we asked ourselves, why is there a need for this tool? Is it only applicable to pandemic scenario education? Hence, how does this fit within normal and abnormal curricula? What needs to be expanded on this tool? Should we look into different labs or additional use cases to really maximize its efficiency as a tool? How do we develop this to cater the broader community, the broader nuclear engineering community, or the broader nuclear community as we try and tackle, this workforce development challenge? And does this tool align with long-term goals such as stated in COP28, tripling nuclear energy capacity and interests? So we asked ourselves these questions. And is it feasible? Well, obviously, for the Geiger counter and attenuation lab, it is feasible, as shown in the previous few slides. But we wanted to expand this, like asked. So, is a virtual neutron detection lab feasible? And is a virtual reactor lab feasible? So let's find out. So the neutron detection lab, specifically here at Purdue, the neutron detection lab, we as students learn to detect thermal neutrons from a neutron howitzer. We use variable sized helium-3 and boron trifluoride detectors. So these gas field proportional counters, variably sized. We look at its effects on the spectrum. And then we learn nuclear electronics operating fundamentals from the preamplifier to the amplifier, oscilloscope, multi-channel analyzer to the high voltage supply. And we pretty much wrote a Matlab script to simulate all that was taught in this neutron detection lab. So we take all this into account and we wrote some code out of it. And so this is a one-line flowchart. Obviously more complicated than the code is obviously more complicated than this, but this serves as a general skeleton and visualization of the code. So let's dive into it. So in the code, we start with the initiation of the simulation. Then we go into initialization. So we set up the detector size, resolution, and other initial conditions. Then we go into parameter calculation. So we compute the detector cross-section, initial neutron energy, gas pressure, temperature, gas constant, atomic density, neutron rate, and other parameters, all that fun stuff. Then we go into reaction and cross-section calculation. So we determine the mass and Q energy of the reactions, along with absorption cross-section and macroscopic cross-sections. Then we go into the core of the Monte Carlo simulation, where random numbers are generated to model the stochastic nature of particle interactions. So this includes determining the interaction probability and distance, calculating energy deposited for each reaction product based on random vectors, taking direction and interaction site into account, adding simulated noise background, adjusting for detector resolution effects if enabled. And then we go into output and visualization, whilst also calculating the detector efficiency. So we plot energy spectra on different scales from MCA channels, voltage, and energy. And in the end, we conclude the simulation. And so during the output, you get something like this in Matlab. So it's like counts against energy, giving you an energy spectrum, and in this case for helium-3. So this is our neutron detection lab's code, the Matlab script that we wrote. So what about the reactor lab? So here at Purdue, for our reactor lab, we utilize the Purdue University reactor number 1. That's what PUR1 stands for. And in this lab, we aim to teach students some fundamentals of neutron physics, such as the point kinetics equation shown here. We also teach students standard operating procedures in terms of reactor operations, from startup to shutdown, moving control rods, such as shim safety and regulating rods. And then in essence, we get students to then observe data trends from subcritical multiplication to criticality to supercriticality. And once again, we took all this into account and wrote a simple Matlab script out of it. And here we have, once again, a one-line flowchart for our code. So we start off with the beginning of the simulation. We then input time and event conditions, so setting the total simulation time and the number of times to change rods with user inputs for specific times of rod movement. We then initialize safety conditions, so setting the initial safety conditions such as scram, setback, and interlock to 0. And then we allocate dimensions, so preparing the arrays to store various simulation parameters over time. And then we define constants related to the delayed neutron groups for our fuel type for the PUR1 reactor. And then we compute the mean neutron lifetime based on these delay fractions. Then we set the starting positions, determining the initial positions of the control rods and other initial parameters. And then we go into the core part of the simulation. And bear with me, this includes generating random noise, receiving user input for rod movement, calculating control rod positions and checking their range. We then get reactivity calculations based on rod positions. Then we solve the ordinary differential equations, ODEs, using point kinetics. We then calculate power, flux, and other reactor parameters. We perform safety checks and adjust rod movements accordingly. And then finally, we output plots. So we print the final neutron count, plot various parameters over time, such as effective multiplication factor, flux ratio, reactivity, and power. And in the end, we conclude the simulation. So we have all these code written down, but we really want to bring our code to reality so users and students can interact with something more lifelike instead of plain code getting these graphs. So we worked with the Purdue Rosen Center for Advanced Computing's and Vision Center. And these are really talented individuals. They are great graphic designers, and it was a pleasure of mine to work with them. So let me show you what we really developed. So we really looked at what most of our devices or what devices students have, such as laptops, computers, iPhones, iPads, tablets, Androids, what these devices have in common in terms of accessibility. Well, one thing we found out, and this is pretty obvious now, that these tablets, these devices all have a web browser, right? We have Chrome, with Safari, with Edge, with Firefox, and we added that with the Neutron Detection Lab, first of all. So nuclear electronics, the neutron howitzer. But it doesn't do justice to tell you what we developed. I would much rather show you instead. So I present to you the Virtual Neutron Detector Lab. And to show you, here is a demo. And I really hope you understand and look at how capable this development is. So without further ado, let's dive into it. So you're able to plug in a nuclear electronics detector, plug it into a neutron howitzer. Do your standard pulse analysis on the oscilloscope with the gains, amplifier. We even have triggered controls included. And you can plug it into your multi-channel analyzer and get a spectrum. Download your spectrum on Excel sheet and analyze the spectrum. So that was the Virtual Neutron Detector Lab. How cool is that? Well, we're just getting started. So once again, we've got browsers, but this time it is not our neutron detection lab. It is the Purdue University Reactor #1. And so once again, we combined it, and it doesn't do me justice or do you justice or do this entire project justice if I told you what it does, but the capabilities of it. I'd much rather show it to you. So I present to you the virtual reactor lab, specifically for Purdue University Reactor #1. And once again, a demo. So booting it up, this was on my Mac, and as you can see, fully accessible on a web browser. And it's as if you're actually in the reactor room. You can look at all the components, all the hardware. You can even peer over the reactor pool. At the main seat, you can look at the all digital INC. And before you begin operating, go through the lab policies and safety quiz. You get tested on stuff like ALARA. And we could really just tailor this to any curricula. And so once you get a reasonable score, you're ready to start operating. You can start off with critical value or shut down or start up. Look at the different data parameters, data viewers. You can select either of the shim safety or regulating rods, hit a target position, and either insert or withdraw. You can stop it. And once you're ready to shut down, you can either choose to gang lower or just do a manual scram. And once you're done, you could download data, choose different data parameters to download or not to download. And there you go. You get a CSV file and you're ready to do your data analysis on either Microsoft Excel or Google Sheets. And this is fully accessible on your web browser. Well, how cool is that? So we've got the proof of concept done. We know that a virtual reactor lab or virtual neutron detector lab or a virtual Geiger counter in an attenuation lab is feasible. But how can we improve? And what are the metrics for improvement? It's one of the things that we're always asking ourselves. So first of all, we want to make this more immersive. Make students feel as if they're actually on site or in scenario. We want something more practical, something that students could use and pick up fundamental concepts within a whim. And most of all, expand it. We want to really expand our capabilities because we're happy with what we have, but we can always improve. So let me bring us back to the first build of the virtual Geiger counter lab. As you can see here, we're not really happy with this. This is all 2D. The figures, the Geiger counter and the source, they all look like they were hand drawn by a child, and the user interface is not very appealing. So how can we really improve on this? Well, I worked with Julian from Envision Center, and he is a very, very brilliant individual. So to make it more immersive and expand our capabilities, what we did first was improve on the Geiger counter. So this is an improved 3D version of the Geiger counter, much better than that hand-drawn Geiger counter we had in the 2D representation of the lab. And then we paired it with the MetaQuest series. We really wanted to make it more immersive. So I present to you the augmented reality gem counter lab. And it does not do me justice, or do you justice, or this project justice once again, to tell you what this development is. I'd much rather show it to you. And so I had Julian here put on the MetaQuest 3 headset, and this is what he sees when he boots up the AR GM counter or survey meter lab. And so this was done in collaboration with the nuclear pharmacy and the nuclear engineering departments here at Purdue. So without further ado, let's start this thing up. So you can scan any environment that you're in, living room, classroom, lab space, etc. You can then distribute virtual sources in any environment. So those yellow things are virtual sources. Pretty cool, huh? Yeah, it still amazes me every time that we've developed something like this. And so from the outside, I really want to show you how you can hear the inverse square law taking place. And this was me putting on the MetaQuest 3 headset. And this is how we hope nuclear education and training will look like a few years from now. There you go. Well, so that was the virtual Geiger counter lab. And I think we've made pretty good progress in terms of making it more immersive, more practical, and even a little bit more expanded. So what's next? Well, remember this? Yes, this is our virtual reactor lab. And so we took this and wanted to improve it. And so we improved it by developing the multi-monitor simulator of the Purdue University reactor number 1. And before I show you what we have developed here, we had to do a little bit of background research. And let me share that with you first. So my team worked with Joyce from the Innovation Center, and she is really gifted and pretty much an expert in user interface design. And so we looked at current simulators employed in industry and really analyzed their capabilities for effective education on a first use basis, these nuclear industrial simulators. So what we did was we judged them. We judged these industrial simulators by a few metrics when it came to an effective educational tool. First of all, we looked at its expensiveness or inexpensiveness. We looked at its hardware, whether it was flexible or not. We looked at its capabilities as a tool for effective education. And we looked at its beginner friendliness. And so we used a 5-star system to judge these industrial simulators according to these metrics. So for inexpensiveness, industrial simulators get 0 stars because they are very expensive. They range anywhere from tens to hundreds of thousands or even millions of dollars. In terms of flexible hardware, we gave them 2 stars because they are really not flexible at all. These hardwares are built to specification, specifically for that power plant. In terms of effective education, we gave them 3 stars. They're pretty effective when it comes to teaching operating concepts and parameters specific to the power plant, but they are not beginner friendly. You need at least an undergraduate to graduate level of understanding when it comes to reactor physics and thermohydraulics. So we developed a multi-monitor simulator. And we judged it by the same metrics as well. So for the virtually integrated labs multi-monitor reactor, in terms of expensiveness or inexpensiveness, we gave it 3 stars. Because Not 5 stars, because it still took us around $2,000 to build. What about its flexibility? Well, in terms of flexible hardware, we gave ourselves 5 stars. As long as you have a computer or a monitor, you are able to boot up our program and use it anywhere in the world. What about effective education? We believe it's pretty effective, but we gave ourselves 4 stars because we believe that we can always improve the way we bring about nuclear education. And beginner friendliness, we gave ourselves 3 stars. Why is that? Well, you still need to learn some basics when it comes to reactor operation, but most of this can be found, or most of the information you need can be found online at the click of a button. So this is the multi-monitor Purdue University Reactor #1 simulator. And it is multi-monitor, as you can see. The bottom left, top left, and top right screens are completely identical to the all-digital instrumentation and control at the Purdue University Reactor #1. Something we can note is that these multi-monitors are fully touchscreen. So students can start off with at a critical value or from startup or shutdown. And these are the monitors that the students interact with, as you can see here. And these are completely identical to the Purdue University Reactor #1's INC. And I'm happy to say that this system will be used by beginner students on their path to obtaining their NRC reactor operator's license. So something students can use and understand how the system works and how the operating procedures work before actually utilizing the Purdue University Reactor #1. So I've gone through a lot so far, and we're happy with what we've developed, but we're still hungry. And we're always asking ourselves, what's next? We're always asking ourselves that. We want to constantly look towards expanding our capabilities. So what's next? Well, here's a hint. And that hint comes with these pictures. So as you can see here, we've got variable size neutron detectors, got nuclear electronics. We've got different detectors such as sodium iodide detectors, and even a GM detector. So I present to you what we're currently developing on, and this is the Virtual Radiation Labs, and this is a team that we're working on, us and Julian. This lab will hope to see all undergraduate labs within the nuclear engineering curricula. We're currently developing, and we've already written code for modular nuclear electronics. We're currently developing the user experience for that. And with this virtual lab, it comes with different detectors as well, from the GM detector to the helium-3, boron trifluoride, and even sodium iodide detectors. And we've got different play modes as well. So we've got a sandbox mode, and students can really just drag and drop modular nuclear electronics, plug and play, and go through different scenarios of undergraduate nuclear radiation labs. We are also really proud to say that we've categorized all the undergraduate nuclear radiation labs here at Purdue. So students can literally click a button and undergo the exact training we receive here at Purdue. Not only that, we also have a challenge mode as well. So students can undergo time-dependent and point-based challenges to really build their radiation detection intuition. So this is something that we're currently developing. And we're always looking for potential collaboration. So feel free to reach out to my student email at lau61@purdue.edu. So that pretty much covers what we're developing and have developed. And here are some key takeaways. Revolutionizing nuclear engineering education is a community-wide effort. We would really hate to be alone in this initiative, so we would hope and love for you to take inspiration from this. And most of all, have fun while at it. This research experience allowed me to constantly question how we should improve our development. How should we make nuclear engineering education or nuclear education and training more accessible? And this has provided me new perspectives every single day, and I had so much fun while at it. Before I end, I would like to introduce you my team, the team that I've worked with. So obviously that's me, Jonah. This is Zenon, and he's from the electrical and computer engineering department. This is Robert from nuclear engineering. This is Trent from nuclear engineering, Shay from nuclear engineering. And we were really, really privileged to work with Julian from Invention Center as well as Joyce from Invention Center. And none of this would have been possible without Dr. Hatzidakis, our PI from the School of Nuclear Engineering. I want to note that 6 out of 7 of us are undergraduates here. So I would really like to stress that with a team of creative and dedicated undergraduates, a lot can be achieved. And last but not the least, I would like to give a special thanks to Purdue Nuclear Engineering for supporting as well as funding some of our projects. And here are my references. Thank you all.
Thank you, Jonah. If you have questions, go ahead and type them into the questions pane. And while those are coming in, we'll take a quick look at the upcoming webinar presentations. In February, the analysis of reactivity loss of the Phoenix core cycles for the experimental validation of the Darwin FR code package. In March, overview of Canadian R&D capabilities to support advanced reactors. And in April, multiphysics depletion and chemical analyses of molten salt reactors. Again, if you have questions, go ahead and type them in. I don't see any questions at this point, Jonah, but let me ask you one if I may.
Yes.
In your simulations, are you also able to simulate reactor safety modes? Can you take things to abnormal events to see how students might respond?
Yes, we are able to. Yes, that is something that we have definitely looked into it. What is hard in terms of that is that the Purdue University reactor number 1 is very, very safe. So we have definitely added some accident classes within our code, but it was not really necessary for us to implement that in terms of user design. It was more on the case where we wanted students to learn the operating procedures. How do I get this reactor up to critical? How do I go supercritical? You know, how do I balance my reactor? But in our code, we've definitely looked at implementing, and we have implemented different accident classes. It's just hard because for the PR1 reactor, it's a light water open pool reactor, and it mainly runs through natural circulation. So even if an accident happens and things get out of the way, with stuff like Doppler broadening and stuff like that, the reactor itself balances out, and not a lot can happen. But that's definitely something we're definitely looking into.
Thank you. A question that has come in is, have you verified the simulated results?
Yes, we have a plethora of data from the PR1 reactor, just because it is an all digital INC. So it all gets packaged in a really nice Excel sheet, and we've done a lot of benchmarking, and I'm happy to say that our results do line up with benchmarked data.
Thank you. So I have another question then. Has
Yes.
Purdue implemented this, or is this still in the development phase? I mean, are they utilizing this for their current undergraduate programs?
Not yet. Well, yes and no. So for the neutron detection lab, we have actually used it in class. So there was this one period when, so Dr. Hatzidakis actually teaches all the undergraduate nuclear engineering radiation labs, basically. And so this one time last semester, our Neutron howitzer, the cart that was on so that we can safely transport it broke down. So it was in the storeroom, and students can't actually, do their lab inside a storeroom, right, in a safeguard room. So what they did was we made so the whole lab for that week just went online. And so what they did was they used the virtual neutron detection lab for the whole session. So luckily we had that, and students were pretty happy with it. So that was a case where it was implemented. And for the multi-monitor simulator, since we're coming up with a new batch of students to train for the NRC operator's license, and with this new batch, they would most likely be using this to understand some concepts, as well as understand the system and understand the SOPs and the procedures to getting, from subcritical to critical to supercritical. They'll be using the multi-monitor simulator first before actually going to the reactor room and learning with the actual reactor operators.
Very interesting. For dynamic situations, do you use your self-written code or some standard nuclear reactor thermal hydraulics code like RELAP?
No, we write our own code.
Thank you. So I'm also very curious. It'll be very interesting to see the statistics of increased interest in student participation within the program. I think it's very exciting to see the next generation and the thoughts that they have to revolutionize how the material is presented and the instruction. So I applaud your team's efforts. I think it's extraordinary, and I just really look forward to what the next generation is capable of and will bring to the nuclear industry.
Thank you. I really appreciate that. And we're looking forward to. We want, we want, as I said, that people can look at this and maybe replicate this, and also just take it to the next step. Just look at this as, this is a proof of concept. This can be done, and do absolutely amazing things with it.
Exactly. So have you shared your endeavors with some of the regulatory agencies? Are you working with state regulators or the NRC? Have they seen some of the work that you've developed?
Well, I believe so. Not personally under me, but our professor who runs the whole lab, and he has other other projects as well going on, and he has showcased the multi-monitor simulator when the NRC was coming by for a tour sometime. So I believe there are talks somewhere, but I'm not quite sure where it is going.
I think the word will be getting will spread now rapidly, so that's great. What code's more usable than what codes are more usable in your job? MCMP, Fluka, GEANT4.
What codes are more usable in my job?
MCMP.
Right. Well, in this code, all of our code are, so the one thing that runs this multi-monitor simulator is we're just using point kinetics, right? Because it's fast, and students can, it's easy for us to develop because everything is run through a Unity web browser, or it's Unity based, so everything is in C#. And so we don't really see the need for MCMP right now, or Gen 4, or whatever it is. Everything is just point kinetics. What we do is we write them all in Matlab. So simple PKE, we convert that to C#, and on C#, that is then, we translate to C#, and C# is then presented through our Unity Web GL or Unity game development program. But in classes, obviously, when we're doing Neutron, our Neutronics coursework and stuff, yes, we do use MCMP and stuff like that. So I don't think that is very relevant to this this project, but we are definitely looking at how we could couple some of these codes with our simulation for sure. Very, very exploratory phase in terms of that.
Thank you. That's the list of questions that have come in thus far. Again, I apologize for the delay getting started this morning. It's always nice to start with a little bit of adrenaline when you log in and don't see what you expect. So I apologize for that. Patricia, do you have any last minute thoughts before we close today?
Yes. I appreciate that you're asking all these questions. Jonah, again, I was amazed a year ago. I'm still amazed by this work. I think to have this webinar recorded and archived on the GIF portal will certainly help in communicating to the US and the world what your laboratory is doing. It's amazing. Thank you very much again for taking the time to present to everyone, and I wish you the best for your complete success.
Thank you so much, Dr. Pavier. It means a lot, and I really appreciate getting this opportunity to present my team's work on here. Thank you so much.
Yeah, excellent. So thank you very much.
Okay, we do have one more question, so let me go ahead and do that before we cut off. Which tool your team is using for graphics development and how the graphics tool is coupled with dynamic simulation tools?
Right, that's a really good question. Well, a lot of our objects and texturing is all done on Blender. So Blender is really, really good for that. And so what we do is we import that into Unity. And with C#, you can couple the objects with the dynamic functions that come with the code.
Thank you. Okay, well, with that, I think we'll go ahead and let people start the rest of their day. And again, Jonah, thank you very much. Patricia, good to talk with you again, as always. And I'll go ahead and conclude. Thank you. Bye-bye.
Bye.
Bye-bye. Bye.